Welcome everyone. Thank you for joining us for today's TASI webinar, Turkish Association for Seismic Isolation webinar. My name is Mehmet Emre Özcanlı and I'm the president of TASI. In TASI webinar series, worldwide reputed seismic isolation experts present on seismic isolation applications in their countries. Today, Professor Dr. Akira Wada is presenting seismic isolation applications in Japan. If you have any questions during the presentation, please type them into the question box in our TASI YouTube channel chat panel. I'll bring them up during the presentation and we will also have time for questions at the end. Especially, I would like to thank Mr. Paolo Clemente, who is Assisi President, as he distributed our webinar announcement to all Assisi members throughout the world. I would like to introduce our speaker, Professor Akira Wada Sensei, briefly. Professor Akira Wada has graduated Tokyo Institute of Technology, TTEC, at 1968 and received master's degree from the same university in 1970. After graduation, he started working at Nikkan Sekkei, the biggest structural design company in Japan. He has worked at Nikkan Sekkei until 1981, and he received a PhD degree from TTEC at the same year. From this point on, Professor Wada Sensei started his academic life at TTEC as an associate professor and promoted as a full professor at 1989. During his academic life, he has joined short-term research projects at MIT or University of Catalonia, Italy. He has been the director of TTEC Structural Engineering Research Center between 1997 2008. Professor Wada Sensei has retired from TTEC at 2011 and assigned as the president of Architectural Institute of Japan, AIJ, between 2011 2013, which is an academic association with about 35,000 members of architects, building engineers, and researchers. Since 2013, Professor Wada Sensei is the president of Japan Society of Seismic Isolation, JSSI. Professor Wada Sensei has published numerous papers and books regarding advanced structural technologies, structural dampers, buckling restraint braces, and seismic isolation. Now, I would like to give the stage to the Professor Wada Sensei.
Thank you very much, very kind introduction, Dr. Mehmet, and Fatih help us always. Thank you very much. I'd like to discuss about seismic isolation application in Japan. And this figure, Dr. Mehmet is constructing now, very large residential house project. I visited just 1 year ago, and we hope to learn and discuss many things from Turkey, and Turkey and Japan are very long friends. And my presentation, Mr. Kani, Mr. Kamikochi, and Mr. Kimura and Shinozaki gave me several photo or data. Return to 1995 and 2011. 26 years ago, a very large earthquake happened in southern part of Japan. This is a railway system. Very severe damage we got. at the time, more than 6,000 people were killed, and many fire and many structures were broken. Just at the time, I was 50 years old. After that, we did many research, and we promote seismic isolation system and passive control structures. And after big earthquake, many structure was broken and garbage was produced. At the time, I think some of them will know, in 1981, Japanese seismic design standard was changed, and we are using same standard almost 40 years. This apartment building is a six or seven story apartment designed by new seismic design code. But this photo was taken after 1995 earthquake. And at that time, this building is not so old, 5 years or less than 10 years old, using new seismic design code. You can see the many cracks around the both end of the every beams. You can find fracture cracks at the both end of the beam, and some X-shaped cracks happen beam column joint. And this cracks is expected by professors, researchers, engineers, also government people. But general people don't know the detail of the damage or cracks. After this earthquake, they demolish this apartment building like this. They have to find new apartment, and they lose many monies. And all trucks bring many garbages produced by collapsed buildings or demolished buildings. Just 10 years ago, tomorrow is just 10 years, 2011, March 11, very big earthquake happened in northern east part of Japan. More than 20,000 people were killed. Very severe tsunami, and some building has also had damages. This building is a Sendai apartment, 12-story steel reinforced concrete structure. And this photo taken after the earthquake. From here, we cannot see any cracks, but there are many cracks around non-structural walls. About thickness is about 10 centimeter, and not so many reinforcement, so many cracks. And this earthquake happened at 3 o'clock afternoon. There were mother and children. The father will not be there. The March 11th was Friday, but mother and children get very severe, and they don't like to live same apartment. Also, this apartment was demolished. The one young professor, Yasushi Sanada, checked the all cracks around the structures. The east frame is there are 12 columns, And 11 non-structural wall. Non-structural wall has a little wider than the column, and the thickness is very only 10 or 12 centimeters, and not many reinforcement. The cracks around the non-structural wall is very large, from first floor to sixth floor. And the west frame, there was door or window, very complicated non-structural wall system. Many cracks from ground floor to 12th floor. Also, this building, they don't like to live after the earthquake. Just 1 month before this earthquake, very big earthquake hit Christchurch, New Zealand. This photo taken before the earthquake, very beautiful country. And there are hotels, office, university, or residence. But after this earthquake, they demolished many buildings. You can see the vacant place. Almost 2/3 buildings were demolished. There is very famous university for earthquake engineering, the University of Canterbury. Gregory Mackley is my friend. He gave me the map of Christchurch. Red square means the demolished building. Yeah, you can understand that 2/3 of the buildings were demolished. Our responsibility and the mission were not satisfied. We are structural engineer and earthquake engineer. But after a big earthquake, many buildings were demolished. I don't like this situation. But the professors in Turkey or Japan, New Zealand, United States recommend ductile frames to students. One very famous professor, he passed away 3 or 4 years before. He is the same years as me. He gave me one photograph and message. This car designed to protect life in the extreme event, but damage is expected. Very similar concept of the ductile moment resisting frame. I showed several photos after the earthquake. Damage is expected, but people's life will be okay. But in the big city like Christchurch or Istanbul or Tokyo, there are too many buildings designed the ductile moment resisting frame. Many buildings will have some damage, and after that, they don't like to use these damaged buildings. The city life will not continue. We have to consider not only one building, but also the total city. I tested almost 20 years ago. Right-hand side is column, left-hand side is beam. This is very ductile reinforcement, but there are many cracks, not only end of the beam, but also beam column joint. Professor Viterbo Bertolo says the ductility is damaged. We have to reconsider how to make more good structures in the earthquake-prone country. New seismic design concept. Human life have to be safe. This will be okay. And the building can use after some repair. People can understand this idea. And some new, very important buildings must be used just after earthquake. Not only the government buildings, but also residential building, houses must be safe after the earthquake. They have to sleep with their family every night. Many researchers said the house is not so important. Government building is more important. But I don't like this idea. House is most important. The left-hand side is a passive controlled structure. Center is a seismic isolation building. And the right-hand side is ductile moment resisting frame. Many cracks happen around the building. Just 5 years ago, West Island, Kyushu, has been a very big earthquake. And this 4-story hospital building was constructed using seismic isolation. There are many natural rubber bearings and red rubber bearings. This is a orbit of the displacement of the seismic isolation superstructure. We measured the total amplitude is 92 centimeter. The displacement is 46 from southwest to northeast. 46 displacement will be largest deformation of the seismic isolation buildings in the world, I think. But this hospital is perfectly okay after the earthquake. And the houses, the base of people life I already explained, maintain function and continuous use, and repairable for building value itself, and no collapse for human life. So seismic isolated structures are needed for housing structures in the earthquake-prone countries. This district, I think 6 or 7 seismic isolated buildings independently. The tallest is 12 or 13 stories. Lowest is 5 or 6 stories. But these buildings were designed by seismic isolation. The natural rubber bearing and red dampers. And when we design the apartment buildings using seismic isolation, as you know, the horizontal force is not so large, almost 10% of the weight. The seismic horizontal force is very small compared to fixed base or conventional structure. So we can use precast concrete system in Japan. And there are many expansion joints. And about 10-story buildings. And when we designed seismic isolated 10-story buildings, design shear force of the superstructure is about 8% to 15%. And the shear force response in isolated layer, including some damping system, about 13% of the total weight. And the floor response will be 0.15 to 0.25 G. Displacement in the isolated layer, 30 or 40 centimeter. But Kumamoto earthquake, 460 millimeter, we have to consider about 50 centimeter, I think. And the story deflection in the superstructure is very small, less than 0.5%. I think more smaller, I think. And the construction cost when the building is 10-story, almost the same construction cost, or small, little cheaper. And Japanese reinforced concrete design system is very complicated. We need many reinforcement, not only vertical, but also hoop or stirrups. The fixed base reinforced concrete is very not so cheap, and the column is very large. And we can use seismic isolation system for 30 or 50-story buildings. There are 3 buildings. This building has 30 story. This is a frame structure. We need piles, and we need very stiff beams connecting each piles, and seismic isolation devices, and another foundation beam must be set on the seismic isolation devices, and we can make superstructure. This is a frame perspective. This idea, the core has many shear walls, but the wide width is not so large, but core system made by wall. I like this system. And the blue is a beam, the perimeter beam and span beam, but core to perimeter frame, only 4 blue beam. When we design this fixed base conventional structure, we need core to perimeter frame beam many, more than 10 or 15 beam we need. But seismic isolated building, we don't need, we need only 4 span beam. Ceiling height is very large, become large, and the planning is very free. I recommend this system, not only Japan, but also Turkey. Also, this building has used natural rubber bearing and red rubber bearing, red bearing, and very ductile steel bearing and damper. There are many rubber bearing and steel damper and red damper, I think. And also, this building can use a precast concrete system, and the reinforcement is not so many. We can use a precast concrete system, and the construction time is not so long. Very quick construction. And when we design around 30-story buildings, design shear force of the superstructure is 5% to 7% of the weight. And the shear force response also 5%. The top floor some 7% or something. And isolated layer, also 5 or 7% of the superstructure's weight. And floor response, the first floor was second, third floor, almost same value of the shear force, almost 7% G, but the top floor, 20 or 30 floor, the 0.25 G. And the displacement of the isolated layer, the 30 or 35 centimeter. This displacement will be little smaller than the 10-story building. The 30-story buildings itself deform. The superstructure is some deformation. So the isolated layers deformation is a little small compared to 10-story buildings. And the story deformation is very small, also 0.5, less than 0.5%. And the construction cost is cheaper than conventional structure. And the column size is small, reinforcement also small. There are many good things. And after big earthquake, the seismic isolated apartment will not have any damage. But the conventional structure has many cracks. And I retired Tokyo Institute of Technology just 10 years ago. Before, during I was professor at the university, I designed several buildings. This is a 20-story steel structure standing on seismic isolation system. This superstructure has the steel CFT columns, but this building has no columns inside of the building, only outside, perimeter columns. So if same building we design fixed base, we need another column between outer column. The total construction cost is perfectly cheaper than the conventional fixed base building. And this is a university building. There is no columns inside. Planning is very free. There are many freedom to design the inside. Many professors and researchers enjoy using this seismic isolated buildings. And but this building, almost 90 meter high, and the width is 16. Very slender building. The corner seismic isolation device will be stepping. We designed the stepping column system at the 4 corners. And Tohoku earthquake just 10 years ago happened, and the Yokohama building moved something, and we only one chance the stepping this rubber bearing. When you come to Japan, Tokyo, I'd like to show this system. Very difficult to explain. And this building designed by Taisei Corporation. And this is the first seismic isolated tall building, taller than 60 meter building in Sendai. The red line shows the floor response. And the ground motion is 300 girls, but the first floor, 10 floor and 18 is less than 200 girls. if this building has not no seismic isolated building, a conventional fixed base, the superstructure's acceleration is 400 Gauss or 500 Gauss. Very good system. And this is also designed by Taisei, very slender seismic isolated prep school in Tokyo. There are also Tohoku earthquake. Ground motion is 100 Gauss, but the superstructure is 60 or 20. Very good performance. And I'd like to discuss about passive controlled structures. We can say damage controlled structures. Left-hand side is building structures. So is yellow frame is primary structure. We can use very high strength concrete or high strength steel now. Also Turkey, I think, same condition. We designed a little slender column or slender beam because the material is high strength. So yellow frame can deform elastically, little large displacement, about 1% of the story height. And we put some seismic members, buckling restraining brace or oil dampers. And the earthquake energy absorbed by this red color seismic members. And the main frame is a little slender and high strength, almost no damage. After the earthquake, we have to check on the seismic members. And there is some problem, we can change and we put a new one. But the building itself will be okay. This idea coming from human body, the collarbone will be broken. The young boy plays soccer, rugby, or judo, but human life will be okay. And this collarbone will okay about several weeks. And the bumper of the bus, when some car crash, but bumper will be broke, but bus itself and people will be okay. And computer has huge, some thunder come to the house, the huge broken, but the computer itself is okay. This is the same idea of the collarbone. We tested reinforced concrete frame with some damping system using this damage controlled structural system. We taken the one bay, 2 columns and 2 beams from the 8-story buildings. And we put this frame on the shaking table. And only one frame is very light. And only one frame is too stiff compared to 8-story building. We need some flexibility and we need some inertia mass. So on the shaking table, we put specimen and some spring and very heavy weight. We shake this system composed by 3 systems. We can make about 0.6 second natural period we can make. And the specimen size is almost the same scale I think 90% of actual structure in Japan, and we need axial force in the column. We put post tension using the rod, and we put a very flexible soft spring washer at the top of the column between the nut and the top of the columns. We applied axial force constantly. And we put specimen and 220 tons inertial mass and the loading beam and some flexibility by the rubber bearing. And the 220 tons inertial mass put on the 4 seismic isolation rubber, very flexible. When we shake this table, almost all inertial force coming from 220 tons inertial mass to blue beam and pink rubber bearing and green frame. And this is a plan view. The dark blue means loading beam, and we put some load cell. And the green is a specimen. And for pink, the rubber bearing, we put between column to loading beam.
Here in the city of Kobe, they preserved this tiny fragment of the devastation they suffered in the recent earthquake. Japan stands on one of 900 active faults in the Earth's surface. And here in 1995, one of those shifted and tore this city apart, killing almost 6,000 people. Take a look at the destruction in Kobe. Buildings collapsed like a house of cards. And some of the worst hit were medium-sized blocks of offices and flats, 6 or 7 stories high, built before regulations were toughened up in the 1970s. There are thousands of these substandard buildings waiting to collapse across Japan when an even bigger earthquake strikes. And scientists are warning that it's overdue.
The problem in Japan is that we have so many old buildings which are subgrade and which does not satisfy the present cause. If we can rebuild all of them, there won't be any problem, but it's too expensive. Nobody can do that. So we are trying to find the best possible and less expensive way to retrofit or strengthen existing buildings.
And it's here today at the National Institute for Disaster Prevention that they're going to test out a new way of strengthening old buildings. They'll be using this enormous 250-ton earthquake simulation rig. Now, what matters here is that great big grey oblong of concrete. It's held up for the purpose of this test by this blue frame here. Now, that grey concrete represents a story in an old, poorly reinforced building in Japan, with perhaps a room there. As you can see, the great big gap in the middle would be a room. The whole thing is placed on what's effectively a great big shaking table, 20 meters by 20 meters square. You can see the edges of it here, these black and yellow diagonals. And the idea is to shake it side to side for all it's worth, like this. And you can see here at the sides how there's scope there for some 30 centimeters of movement from side to side. In this first test, just look what happens to a traditional, poorly reinforced structure as it's put through the stresses of a Kobe-style earthquake. It rocks back and forth, and the concrete quickly cracks. If it wasn't for the blue steel safety columns, the whole structure would come crashing down. Now they know what happens to these kind of buildings in a Kobe-type earthquake, they're ready to test new retrofitting technology. They wire up another sample with laser sensors and transducers, which can all be monitored from the control room. And into that structure, they add a new damping system. It's the brown and blue pillar in the centre of the picture, an extra column specially designed to absorb the energy of an earthquake. So this is the whole secret of the new system. Here's that central column, and here coloured blue here are two steel plates, one coming up from the bottom, one coming down from the top, as fingers of steel, which don't quite touch each other, because in between those fingers is a very strong viscous material. You can see it just black in between there. When the earth quakes, that warms up and gets flexible, and that allows those plates, those fingers of steel, to move on each other, thus providing damping and stability for the whole building. Engineers from all over Japan are here to watch the test. They've done their sums, but now the moment of truth is approaching. So the test's going to begin any minute now. The red light's on, the alarm's been sounded. Watch the concrete block. If it cracks at all, the test has been unsuccessful. If it stays complete at the end of this minute or so of earthquake simulation, then that damper in the centre there is working. There it goes now, and there's something like 4.3 gigawatts of power driving this electric motor, driving this huge 20-metre square electric earthquake table now as it goes. Is that concrete going to crack? So far, so good. So far, so good. They're clapping. I think they think it seems to have worked. Certainly no sign of a crack in that concrete. No sign of any cracks? No. So what do you think?
It is a real success.
A real success?
As most of the people over there expected, this energy dissipating apparatus worked.
All the waiting engineers rush in to have a closer look and see exactly what's happened to the concrete. And you can see for yourself, there's no damage. The upright concrete columns aren't under as much strain. This is all thanks to the new damping device absorbing the energy from the simulated earthquake. Computer printouts confirm a great result. Next, they remove the blue damping device, ready to check that the structure will collapse without it being in place. You can see the gap between the brown column where they've now taken it away. Let's see what happens without it. So after this day of tests, the Japanese engineers know they've got an answer to making thousands of offices, schools and hospitals across Japan much safer for when the next quake comes. And they can fit those damping pillars without gutting whole buildings. But will they be able to do it in time?
And this test was about 1998. More than 20 years ago. And this is a buckling restraining braces. We tested 1987, 34 years ago. And there are 5 specimens. All specimens have same core steel plates. You can see only the joint plate, the left-hand side and the right-hand side. And 5 specimens has a different steel tube. Left-hand side is more large rectangle steel tube, and more right-hand side is more slender steel tube. And the steel tube and the core member, between core member, we put a mortar. And around the core steel plates, only 1 or 2 millimeters very flexible rubber put. So when tension force in the core steel rod member, only steel plate will be elongate. And when we apply compression force, only the core member shrink. But outer tube is strong and stiff. The no buckling behavior will not happen, but the outer tube is very slender. And when we apply a compression force in the core member, the total system will deform like this buckling. The outer tube's Euler buckling load is greater than the yield force of core steel plate. No buckling will occur. This is 34 years ago idea. And after that same idea in the United States, China, Turkey, or Taiwan, many countries use this idea. And we started to design these 3 buildings in the right-hand side of the photo. Just after we developed buckling restraining brace, we designed this building before Kobe earthquake, about 1990, and constructed after the Kobe earthquake, but design started before Kobe earthquake. This building has many buckling restraining braces. And when earthquake come, beam and column will be okay. Only we have to check buckling restraining brace. And we put some sensor, not using electricity, but very simple deformation sensing system. We put all buckling restraining brace. After a big earthquake, we can check the maximum elongation using this very simple measurement system. And if there is some problem, we can check and replace of new buckling restraining braces. And Professor Robert Park and Professor Thomas Foley introduced ductile moment reinforced concrete frames in earthquake-prone countries about 1970 or something. They said this design procedure is capacity design. Japanese professors and engineers import this idea. I think Turkey also imported, and China, United States. They use this ductile moment resisting frame, not only reinforced concrete frames, but also steel structure. And these two professors at Canterbury University. Canterbury University is in the Christchurch. As I already explained, 2/3 of the buildings were demolished. They used this idea. And also 10 years passed, and they rebuilt new building in Christchurch. They use BRBs and seismic isolation, and they don't like tall buildings. Very similar idea we are studying in these 30 years. And at that time, they said ductility is not final goal. I think ductility of the buckling restraining brace is important, but the ductility of reinforced concrete frame, I don't like. And ductility of steel frame also, I don't like. After the earthquake, there remain many damages around the beam column joint. And, no, I think in Turkey also same situation. structural engineers and architects design some building, they are thinking only their building, but the people don't want to return to the damaged buildings. And when many buildings were demolished in the city, we cannot stay in the city, and we cannot say that we make a resilient city. The structural engineer and architects and researcher have to consider one building independently, not a good idea. We have to think about the city. We have to consider not only the resilience of a building, but also resilience of a city consisting many buildings. Then we have to use seismic isolation system or passive control structures. And Dr. Mehmet and Fatih also promote seismic isolation and passive control structure in Turkey. I'd like to discuss with you continuously. And we, as structural engineers, have a mission to make the world a better place to live. Thank you very much for your attention.
Thank you, Professor Dr. Akira Wada Sensei. Yes. We will go ahead and take some time for questions now. Just a reminder, please be sure to type your questions into the question box in your control panel in TASI YouTube channel. It looks like we have a few questions. I would like to... Okay. Professor Mustafa Erdik asked one question. Thank you for the excellent and informative presentations. Why are rubber isolators preferred much more than the friction pendulum types in Japan?
Oh, what is... I think EPS want to sell their products in Japan, but in Japan we need some permission from the government. Dr. Victor Zayas don't want to make the document for Japanese government.
Understand.
So very difficult to import their technology, but Nippon Steel make very simple friction pendulum system. Almost 5 or 6 years ago, many projects use this system already. Yes.
And also another question. Also, I would like to say that from many countries, many people, many engineers attended your webinar. From Bangladesh, from Somalia, from England, from United States, Italy. So Dr. Martelli says his greetings to you.
Thank you.
Martelli. Also, Tolga Önal from Kavakin, he asked one question. Thank you, Professor Wada. What is the major task for Turkey in order to spread the use of seismic isolation from your point of view? How can we promulgate seismic isolation throughout Turkey? What is your thoughts about?
ちょっと意味、ファティさんもう一回。
Mehmet Bey, Türkçe bir daha sorar mısınız? Size zahmet.
Hocam yani Türkiye'de nasıl yayabiliriz diyor Tolga Oynal Bey bu sismik izolasyonu.
はい。川金のトルガさんの質問ですけど、
Mhm.
メシンとか精神技術をトルコで増えるため、どうすればいいですか？おすすめがありますか？
Okay. In my presentation, I forget to explain. Many building owner or people consider on the initial cost, construction cost, several percent expensive compared to conventional sometimes. But we have to consider the cost of after big earthquake. The total cost is, I think, 1/10 or something, very cheap. I have to explain the total life cost. Then this is important for the understanding people.
Evet, evet. Life cycle cost, yani yapının ömrü boyunca olan maliyetini hesaba katınca aslına bakarsanız deprem yalıtımı ve sönümleyicili binalar gibi binalar aslında o şekilde hesaplanınca daha ekonomik olduğu anlaşılıp yayılma ihtimali var. Evet.
Also another question from Başak Boduroğlu, Miss Başak Boduroğlu. First of all, thanks for this event. Could you briefly talk about seismic isolation methods that are applied to existing buildings for strengthening them?
Yes. I think first project is in the United States, Salt Lake City Hall, I think. And in Japan also, we apply many important buildings or historical buildings. We put seismic isolation devices. Just 1 year ago, we finished 20 years project of Japan Bank old building, older than 100 years old, but very beautiful. Japan Bank has much money, so very easy to pay. They print money and they give money to the construction company.
And also, Yusuf Murat Sezer asks, do you have any specific regulation code for structures intended to be built with seismic isolators in Japan, or is it within include building standard law?
Yes. For first 20 years from 1980 to 2000, we have to get some special permission, but very difficult to get the special permission. We need 2 or 3 months. Many professors ask to the engineers, but after 2000, we have more simple calculation system, almost the same procedure for the not seismic isolation building. But the tall building, we have to get a special permission.
Understand. And also Alessandro Martelli asked a question. In Italy, we had the first application, but not question, just comment. In Italy, we had the first application of seismic isolation and energy dissipation in 1976 to bridges and in 1987 to buildings. However, people here understand seismic prevention less than in Japan. Also, Dr. Fatih Sütçü asked one question. He said, I have a question. Do we teach seismic isolation to engineers during bachelor degree, or do engineers learn it during master's or PhD? Or maybe they attend special training in the company?
Tokyo Institute of Technology, University of Tokyo, Kyoto, a very large university. The professor can teach to the student how to design seismic isolated building or passive control. But a small private university, I think no professors who knows well. And go to big company, they can study on the job. But very small company or rural company, there is no specialist for the design of this new structural system. We are, I think, Mehmet-san also same. We have to make some seminar to the beginner.
Understand.
This is very important.
But how about during the bachelor degree or master degree?
Master degree. And graduate, undergraduate course, they need to learn many things.
Okay.
Very difficult to, master course, I think. Yes.
Courses. And also, Hazem Hijazi asks, what is the difference in the cost between isolated and non-isolated buildings? Approximately, maybe.
Total cost?
Difference.
Difference
between their costs. Isolated and non-isolated.
I think Dr. Mehmet will know very well. If the building is only 5-story, we put some isolation devices. We need another 1 floor. This is very expensive. Device also not cheap, but more 1 floor. And we excavate the foundation. So this is differences of the conventional structure, I think. But in Japan, the building total price and the structural cost is only 25%. When we put we use seismic isolation system, the total price will not change so much.
Maybe EQ.
Yes.
If you do value engineering.
Yes. And the permission process is a little complicated. Conventional structure is very easy to get the permission. But seismic isolation,
yes.
Government people don't know where. We have to teach the government people.
Yes, first. Okay. Also, Hilal Günay asks, Ms. Hilal Günay, what can be said about expansion joint in large mass structures with isolation? Should expansion joints be applied or the structure be left in one piece? What are your observations on this?
Just 1 month ago, one earthquake happened, magnitude 7.4 in the east-north places, almost same place in 10 years ago, big earthquake. There are many seismic isolated buildings, and we visited 3 days. The seismic isolation device is okay. Superstructure also okay, but only expansion joint has some trouble. The architects want to make very beautiful seismic expansion joint in the old normal condition, but very complicated or too sophisticated. But I like more simple expansion joint. Simple expansion joint, no problem. But too beautiful expansion joint is not so good.
Okay. And it means that we have to make our buildings one piece as much as possible.
Yes, yes. Simple is best.
And also Professor Dr. Peyman Narjabadifam. I don't know, you know him? Peyman. Greetings everyone, thanks to TASI and JSSI. Special thanks to Professor Wada for his nice presentation. I will kindly ask him to suggest some actions toward improving the effect of seismic isolation in the whole world. In my humble opinion, we need an international association and JSSI can better manage this. Thanks again.
Okay.
Just comment, but I can say that we have international association
Yes.
called ISISI.
Yes. Thank you very much.
Fatih Hocam tam anlayamadım ama Hilal Hanım'ın sorusunu.
Hızlıca sorabilir miyim? Professor Wada, I'd like to just repeat the previous question by Ms. Hilal Günay. So I will just ask in Japanese for saving time. 建物は幅が大きかったら建物を割れる必要がありますか？エクスパンションジョイントというのは周りのエクスパンションジョイントじゃなくて建物を2つ3つに分けるエクスパンションジョイントです。メイン新建物はどうしたらいいですか？
Okay, okay. I mistook understand.
いや、大丈夫です。
I think biggest seismic isolation building length is 300 meters of the one building. During construction, concrete shrink. So when construction procedure mistook, I think many cracks in the superstructure. But separately make finally only 5 meters part after complete two buildings. Between two buildings, we connect together by concrete. When we make many expansion joints, different displacement will be occurred during earthquake. We need two large expansion joints. I prefer the one body. But the construction procedure, we have to make care. But not so very difficult. Separately construction, and after that, we connect. Finally, we don't need the expansion joint in the superstructure.
Thank you. Again, comments from Alessandro Martelli. The first Italian application of seismic isolation to existing buildings was at the beginning of the years 90s. The first European application of a sub-foundation was in 1998. Also about costs, Dr. Martelli says, in Italy we experienced that the additional cost due to the isolators may be very limited if existing buildings because of savings on the superstructure. He says.
For retrofit, this is very expensive. But Italy and Turkey care the very historical buildings. Historical buildings is very important. So,
it's very important. And also, Professor Peyman Narjabadifam, he asks some actions toward improving the effect of seismic isolation in the whole world. Can you recommend any actions to improve the effect of seismic isolation in the whole world?
Promote whole world. I became 75 years old just 2 months ago. I have 25 years until 100 years old. I'd like to visit many countries, promote seismic isolation idea. Please invite me, and I'd like to go.
Also, I couldn't read the name because AA, just the nickname maybe. Can we say minimum required percentage per hysteretic damping ratio to the sum of the energy dissipated by viscous damping in the main structural elements and supplemental dampers for existing building retrofit?
Yes.
If you want, I can repeat.
And this is not the seismic isolation building, but also passive control.
Yes, passive control.
In Japan, steel structure itself has 2% damping, not consider any supplemental damping. And reinforced concrete will have 3%. And we add some dampers. I think steel structure originally 2% to 5%. Not some engineers said 20% damping system, but I think this is very difficult. 5 plus 3%, total 5%. I think, but very effective.
And also, Dr. Martelli corrected one thing. He was talking about additional cost about new buildings, not the retrofit.
So, and this idea, after the earthquake, we check only the damping system. This is very effective.
Okay. Also, can I ask one question? Also, I would like to know about the insurance policy in Japan. For example, if you isolate one building, how about the earthquake insurance rates? Or if I apply isolation, the government can maybe apply any encouragement, incentive?
Yes. If the building is seismic isolated, the insurance every month or every year, some owner have to pay to the insurance company. This is cheaper than the normal fixed base building. Seismic isolation building is a little cheaper.
Okay. Also, again, Professor Peyman, of course, Assisi is the effective in this field, but referring to the beginning of and closing sentences in the presentation, maybe we need to focus on seismic isolation separately. Okay, just comment.
Okay.
Also, Gökhan Yazıcı from Kültür University. I would like to ask if the seismic isolation systems in existing buildings built earlier than 2000, as the displacement demands have been increased considerably in recent design codes.
ちょっとファティさん、どういう意味？
最近の基準は、変形が大きくなりましたって質問があるんですけど、でも日本は1981年からは基準は変わらないですね。
そうですね。The displacement story deflation criteria is not changed. But Japan, East Japan big earthquake happened 10 years ago. The one building in Osaka, 700 kilometers from the epicenter, moved plus minus 1.5 meters. Total amplitude is 3 meters. Very large displacement. but the regulation or code or standard, they define only story deflection angle. I think Turkey also in Japan. But the people living in the top of the building move plus minus 1.5 meter, not only east-west, but also north-south. Very scary. They, I think I told before Dr. Mehmet, they living in the top of that building, see the yacht and the crowd. The building move like this. Very large displacement. I think total displacement and the total angle we have to check. Very scary. Young lady don't like to stay this moving structure.
Thank you. Also, another question, specific question, Mehmet Gündüz Kuduoğlu. During the earthquake, do you know any maximum horizontal movement, ground motion movement? He's not talking about the fault movement. Just due to the ground motion, maximum horizontal movement in centimeter or meter.
Displacement.
Yes, displacement.
I think I don't know.
Just the ground.
And, as you know, when we make numerical dynamics analysis, we don't need any ground displacement. We need acceleration record.
Yes, I know.
I don't know the ground motion itself.
Also, again, Dr. Paolo Clemente says his greetings to you.
Thank you.
He was with us. Ozan Pınar, I would like to celebrate your new age and wish you an endless healthy life. I believe the science and so the engineering improve better and rapidly if a mass public request and support exists. Also Fatih Sütçü, Dr. Fatih Sütçü, bearing capacities has been considerably increased, so now we can use smaller bearings. Buildings in the past were built with larger bearings. Yes, also, again, Professor Peyman, what Professor Wada thinks about the practical application of shape memory alloys in seismic isolation, especially regarding recent progress in low-cost iron-based alloys?
I read the paper of the shape memory alloy, but I have not experienced to make some study. I visited Ashiji, very beautiful cathedral in the Ashiji. They put the shape alloy, shape memory alloy. They use the retrofit of the building. Italian people use many new materials. I respect Italian people.
Thank you very much. Ozan Pınar asks, what is the percentage of Japan's public society which are aware of the seismic isolation technology and request their new houses to be built seismic isolated? What is the percentage?
I think I don't know the number of the building, but total floor area in the world in 1 year, I think 5 or 10% floor area constructed on the seismic isolation.
And also another question, for frictional dampers, Can we say a recommended ratio between slip load and yield load for bolted buckling restraint frames for retrofit of existing buildings?
BRB?
For
Retrofit.
dampers, can we say a recommended ratio between slip load and yield load for bolted buckling restraint frames for retrofit of existing buildings?
Using buckling restraining brace will be cheaper than the seismic isolation. I think seismic isolated retrofit is not so many in Japan. Only government building or very important building. Private building very difficult. BRB it will be very easy to use.
And also, last question, because in Japan it is very late.
No, it's okay.
That's the last question.
Okay.
Compared to Japan, where are we and how much time do we need by means of public awareness?
ちょっと意味がわかんないな。ちょっとファティさんどういう。
パブリックアウェアネスというのは、国の人々はこの免震技術を気づくにはどのぐらい時間がかかりますか？やっぱり自信が必要です。はい、どうぞ。
そうですね。When earthquake happen, many residential buildings use seismic isolation. But after 5 years, very small number. Large, small, large, small. No. But in the future, I think in this next 30 years, more than 70% big earthquake will come to Tokyo. If before big earthquake, some good building owner make to build a seismic isolation building, some not good, clever people use conventional structure. Before 30 years, big earthquake come, the clever people will be safe. Not clever people lose much money and buildings.
Yes. And also some comments again from Dr. Martelli. As Professor Wada said, the upper basilica of San Francis of Assisi was retrofitted with shared memory alloy devices between transept and the two tympana after the 1997 and 98 Umbria Marcia earthquake. Says,
okay.
Comment. And Kurtuluş Atasever, is it possible to attach seismic dampers externally to reinforced concrete beams or frame, maybe?
最後なんて言ったんだろう。
先生、ダンパーを建物に外からつけるんですけど、直接針につけられますか？
そのシェイプメモリアロイの場合？
いやいや、ただのダンパー、例えば、座骨高速ブレースとか。
やっぱり何かフレームをつけて、その中に入れて、でそのフレームを既存のフレームの中に作るって、ファティさんの方が詳しいんだ。
Yeah. Professor recommends to attach an additional frame to the exterior of the existing building and put the dampers on the additional frame instead of directly implementing the dampers onto the beams.
Okay. And now it looks like we covered all of our questions. I really appreciate you, Wada Sensei.
Thank you.
Is there anything else you wanted to cover before we finish, Wada Sensei?
Thank you very much. And next year, I'd like to visit Turkey, Italy, many countries. Thank you.
We will be glad to meet you. Great. Thank you, everyone. We appreciate you being here. We will continue webinar series. Therefore, please follow our social media accounts for our next webinars. Thanks again for joining us today, and we will see you next time. Thank you.
Thank you.
先生お疲れ様です。
どうも。
Wada-san